This fourth podcast on acids and bases deals specifically with bases, both strong and weak bases. When a strong base dissociates, it's much like a strong acid. It dissociates 100% or close to 100%. So here's an example on the screen of a strong base, and it will lose its metal, that's what the M stands for, and then the OH minus goes into solution. Strong bases are typically your group 1 hydroxides, all of them, and 2 are listed here, sodium hydroxide and potassium hydroxide, and they're very soluble and they're strong bases. Group 2 hydroxides are also strong bases. They're a little bit less soluble than the group 1s, and it's mainly the 4 that you see here: calcium, barium, magnesium, and strontium. You can calculate the pH of a strong base directly from the concentration of the base in the solution. So you simply take the OH minus concentration, assuming the base dissociates completely, and then you use that to calculate the H plus by using the kW, and then from the H plus you can then get the pH. So it works pretty much like a strong acid. Now a weak base is a little different. The weak base reacts with water, and so it produces a conjugate acid and a hydroxide ion, and this is a typical weak base reaction. Weak bases many times are ammonia derivatives, so you can see here on the screen CH3NH2. It's basically a nitrogen with 2 hydrogens and then a carbon group attached, so it's kind of like your NH3, but one of the H's has been replaced by a carbon group. So CH3NH2 is a pretty typical weak base, picks up a hydrogen from the water, you produce the cation and OH minus, and then that reaction would have a Kb at a particular temperature. So you could set up your Kb expression with your products over your reactants raised to the power of your coefficients. So much like a weak acid, except we typically put water into the reaction, and a weak acid reacts with water too, but you can, because of the reaction, leave the water out. Here we put the water in, although in the Kb expression, remember, because water is a pure liquid, it does not end up in there. Now, Kb is for some common weak bases. Notice ammonia's up there at the top, 1.8 times 10 to the negative 5th. And it looks like they go as low on this table as 3.8 times 10 to the negative 10th. And these are all ammonia derivatives again. Same idea applies with Kb. The higher the Kb, the stronger the base. The lower the Kb, of course, the weaker the base. Now, if we were to try to actually calculate the pH of a weak base, as we did with an acid, we would want to react that base with water. So we're using a generic B for base. The base picks up a hydrogen, producing hydroxide, and then of course we can write the Kb expression from that, products over reactants, and then leaving the water out. All weak bases do this, okay, so it doesn't have to be difficult. The base reacts with water, pulls the hydrogen off of the water, and you get OH produced. Now if we take an actual example, this is ammonia, and we want to calculate the pH of a 0.5 molar solution of ammonia. Just as in with the Ka problem, we want to write the equation for the reaction. So we're going to take the NH3 and we're going to react it with water. The hydrogen comes off the water, so we get NH4 plus produced, and then OH minus. Now, just as with the weak acid, we want to put this into an ice table, and it looks like we're starting with 0.5 of the NH3, none of the NH4 plus or the OH minus, and so that NH3 is going to go down by X, and then each of the products there will go up by X. We can then add those together to come up with our equilibrium concentrations, and then once again, as with the weak acids, we can plug these into the Kb expression. Now once again, the 5% rule says that we can eliminate the change in X on the bottom, assuming it's really close to 0, and then solve this problem algebraically. So 1.8 times 10 to the negative fifth equals x squared over 0.5, and then solve for x, and as long as that x is less than 5% of what we would have subtracted it from, it's a pretty good estimate. Once again, if this isn't something that you want to do and you actually want to graph this or use the quadratic, feel free to do that, but this is a real quick estimation method. And then of course we're going to solve for x, and our x ends up being 3 times 10 to the negative third. Now be careful when it's Kb, because that means the x is actually the OH minus concentration. So we need to put a little extra step in here to get the pH. So we're going to take that OH minus, and we're going to negative log it. That 2.52 that you see on the screen there actually represents the pOH. And if you'll recall from a previous podcast, pH plus pOH equals 14. So if we perform a quick little subtraction here, if we take 14 minus the pOH, the pH of that 0.5 molar solution of NH3 then will end up being 11.48, which of course then is a base.